Hello, and welcome to Chem Talk. Today, we'll be learning about R and S configuration, a super important labeling system used in organic stereochemistry. Even though this system may seem trivial, it has powerful effects. For example, in this lecture, we'll learn about thalidomide, a drug used to treat morning sickness. R-thalidomide, or the thalidomide drug in its R configuration, works as an effective treatment. But S-thalidomide, its enantiomer, is known to cause birth defects in newborn children. Alright, let's talk about it. R and S notation is a method of determining the direction of connectivity of substituent groups around a chiral center in a molecule. The letter R represents clockwise substituent groups, and S represents counterclockwise substituent groups, which we'll get into soon. These letters can be used both to determine the stereochemical relationship of two molecules and can be used to differentiate between two enantiomers in naming. To assign R and S to a molecule, the very first step is to identify the chiral center or centers of the given molecule. In our first molecule, the carbon is our chiral center. In these three rightmost molecules, the chiral center is right here, so we'll identify those. The next step is to order the substituent groups in terms of priority, which is done simply by atomic number. The first priority group is the atom with the highest atomic number. The second is the second highest, and etc. When assigning priority, if two groups attached to a chiral center have the same atomic number, we'll look at the groups attached to those groups. If there's a tie there, we'll look at the highest priority group attached to those, and so on and so forth. I know that may seem confusing, but stick around to the examples to learn more about that. In our first example molecule here, fluorine, F, has the highest atomic number, so it is the highest priority, and we'll number it 1. The next highest is oxygen, so that's 2. Then nitrogen, which is 3, and finally hydrogen, which is 4. So that's how we number that molecule. In these rightmost molecules, our chiral center is attached to the same 4 groups. A hydrogen here, a bromine here, a propyl group, and here a methyl group. So, across these three, the numbering will be the same. We'll have a bromine, a carbon, and a hydrogen. Across all of these, the bromine will be the highest priority, priority 1, because it has the highest atomic number. The second highest atomic number substituent is carbon, but we have 2 of those. So, what we'll do is look at what those carbons are bonded to. This carbon here in the propyl group is bonded to, besides our chiral center, a carbon here and 2 implied hydrogens. The other carbon substituent group, the methyl, is bonded to 3 hydrogens in our chiral center. So, if we compare the two, this carbon, the propyl carbon, will get the higher priority, priority 2, because it's bonded to atoms with higher atomic numbers. The other carbon, the methyl carbon, will be given priority 3. Even if that concept is still confusing, we'll see more examples as we go along, so be sure to stay along with the video. Finally, hydrogen has the lowest atomic number, so it'll be given the lowest priority, 4, in all of these molecules. Again, in these rightmost molecules, the numbering will be the exact same because we have the same substituent groups around the chiral center. The bromines will be the highest priority, priority 1, followed by the propyl carbon, which is 2, next the methyl carbon, which is 3, and finally the hydrogen is priority 4. The third step is to orient whatever our lowest priority molecule is to the back. So, the molecule which we assign the number 4 should have wedges coming towards it, meaning again it is pointed to the back. In this first molecule, hydrogen, our lowest priority substituent, is already oriented to the back, so we can move on. On the right side, in this topmost molecule, again, our 4th priority substituent is already pointing to the back, so we're done with this step. However, in the middle molecule, we have a different problem. Hydrogen is in the plane and not pointed backwards. To get it to the back, we can rotate around this bond because there's no pi bonds, so we have free bond rotation. If we rotate this section of the molecule, we can do so such that the carbon group goes from forwards to in the plane, the bromine goes from the back to the front, and the hydrogen goes from in the plane to the back. I know that's a bit hard to visualize, so I'd recommend using a molecular modeling kit or an online 3D modeling resource to visualize this and better understand what happens when we rotate this particular bond. Once we rotate, we'll find that we're left with the topmost molecule, and the hydrogen is in the back. The third situation we might encounter is one where our lowest priority substituent is coming towards us, like in the bottom right molecule. In these situations, we have two options. We can either rotate around a bond, like we did in the previous situation, to get the lowest priority substituent to the back, or we can visualize what it would be like to see this molecule from the other side. In this case, if we looked at this molecule from the back, hydrogen would be in the back, which is what we want. Our fourth and final step, then, is to assign R or S. To do that, we look at the order of the numbers 1, 2, and 3, which we've used to number the substituent groups, after we've put item 4 in the back. If substituent groups 1 through 3 are oriented clockwise, the molecule is R. If groups 1 through 3 are counterclockwise, the molecule is in its S configuration. So, we can do the last step in assigning R and S for all of these molecules. Here, the groups are clockwise, so this chiral center is R. In the top left molecule, the groups are counterclockwise, so the chiral center is in its S configuration. The same goes for the second molecule, because, again, we established that if you rotate around this bond, the molecule is the same as the above one. For the last molecule, again, we can either rotate the molecule around this bond until hydrogen is in the back, in which case we get the first molecule at an S configuration. Or, if we look at the molecule from the back, then hydrogen is oriented to the back and we can assign R and S from there, and we'll get the same answer, S. Here, let's number the substituents. Bromine again is first, then the propyl group, then the methyl group, and finally our hydrogen. And we can see that hydrogen, our fourth substituent, is pointed back. From here, again, we can assign R and S by looking at the directions of the 1, 2, and 3, and we see that this molecule is, like we confirmed, in its S configuration. In scenarios like this, when the lowest priority substituent is in the front, as in the bottom right molecule, a common and popular trick is to assign R or S to the substituents 1, 2, and 3 with the lowest priority molecule in the front, so we leave it as it is, and then switch the letter. For instance, here, if we assign R and S with H in the front, we know that it's the opposite of what we get when looking at the molecule from the back. So, here, we can assign R and S, and we get R, but we flip it because H is in the front. So our final answer will be S, which again matches what we got the first two times. Now, we've proven something. Because all of these molecules have the same connectivity, that is, they're stereoisomers, and their chiral centers are all the same R or S, they're all S, we've proven that all of these molecules are identical. Okay, let's take a look at another two example questions. In this molecule, again, we'll start by identifying the chiral center, which is here. Then we number the substituent groups. Number 1 is nitrogen because it has the highest atomic number. Next, we have two carbon groups. The leftmost carbon is attached to a carbon, a hydrogen, and a hydrogen, whereas the rightmost carbon is attached to 3 hydrogens. So our leftmost carbon will be given a priority of 2, and the right carbon will be given a priority of 3. And finally, we have an implied hydrogen, which we can draw in here and give a 4. Now, we can check and make sure that our lowest priority substituent is in the back, which it is. Our hydrogen is pointed backwards, so we don't have to do anything for that step. If we look at the direction of 1, 2, and 3, they are in a clockwise orientation, meaning this molecule is in its R configuration. Let's take a look at the second example, which is a little bit more complex. So, first step is to identify our chiral center, which is right here. And next, we'll assign priority. Each of the substituent groups coming off of our chiral center is a carbon attached to a carbon, a hydrogen, and a hydrogen, like so. So, all three of these, right now, have the same priority. In cases like this, where everything is the same priority, the next thing we'll do is move to the next substituent group. So, we'll move one down from each, which I'll mark using these green dots, and we'll check what these carbons are attached to. Our uppermost carbon is attached to a hydrogen, and a hydrogen. The rightmost carbon is attached to a carbon, a hydrogen, and a hydrogen. And our lowest carbon is attached to a carbon, and a carbon. Because our lowest carbon is attached to the atoms with the highest atomic numbers, it is given the highest priority, number 1. Rather, that side is given the highest priority. Our rightmost carbon, which is attached to a carbon, a hydrogen, and a hydrogen, will be given the second priority. Again, though, we're giving it to that side, not necessarily that particular carbon. And our third carbon group, the uppermost carbon, will be given a priority of 3. Our last molecule is our implied hydrogen, which in this case is facing forwards. So our lowest priority molecule is coming towards us out of the plane, and we can use the trick we learned in the last slide. What we'll do is assign R and S in the situation we're given. 1, 2, and 3 are oriented in a counterclockwise direction, so this molecule is S. However, because our lowest priority group, again, hydrogen, is coming towards us, we can simply assign R or S and then change it to the other one as if we're envisioning the molecule from the back, like we did again in the last question. So, here, our groups are oriented in a counterclockwise manner, so at first glance we would assign S, but we have to remember that our lowest priority substituent is coming towards us, not in the back, so that S is actually an R. So, for this molecule, our answer is R. Let's tie what we've learned back into the application we discussed at the beginning of our video. Here, we have 2 different enantiomers of thalidomide. If we use what we've learned, we can assign R and S to these enantiomers. Our topmost molecule is R thalidomide, and the bottommost molecule is S thalidomide. Again, even though these 2 molecules have the same connectivity, because they're enantiomers and have different R and S, they have entirely different and potentially catastrophic effects. A difference in enantiomers, just molecules with a different order of connectivity, is the difference between a drug that relieves morning sickness and one that causes birth defects. The structural difference in these 2 molecules changes the way it interacts with other molecules and things like that, which causes different effects. So, the difference between R and S molecules are of note throughout medicine and chemistry as a whole. In summary, we learned that R and S is a system useful for differentiating between enantiomers in naming and in identifying the stereochemical relationship between molecules, whether enantiomers or diastereomers. We learned the steps for assigning R and S to a molecule, and we learned that a pair of enantiomers, such as R thalidomide and S thalidomide, can have entirely different effects. Thank you for watching, and be sure to check out our website chemistrytalk.org for more great chemistry, biochemistry, and organic chemistry tutorials and content. If any of the terms in this video are new to you, check out our other videos on organic chemistry and general chemistry for more help.